This video is a definitive workflow and reference guide for 3D microstructure fabrication using the 2-photon polymerization or 2-photon photolithography method, often called 2PP or TPP. The core ingredients for a 2PP system involve three main components: hardware, optics, and chemistry. Hardware includes a near-IR femtosecond laser with specific wavelength and pulse characteristics. Optics requires a high-NA microscope objective focused directly into the liquid photoresist. Chemistry relies on negative tone acrylate resist for fast cross-linking and development. The standard fabrication workflow consists of 4 phases: digital, prep, print, and post. Digital involves CAD and slicing. Prep includes choosing the resin and preparing the substrate. Print is the execution phase where the laser is optimized. Post-processing covers development, drying, and finishing. In the digital phase, convert your CAD design to an STL file, then use job prep software. Standard slicing and hatching steps are typically set between 0.2 and 0.3 micrometers. For large solid structures, a shell and scaffold filling is recommended to reduce print time by about 2.7x, but overly sparse settings should be avoided. When choosing acrylate chemistry, you can take a commercial route using proprietary resists like IPL 780 or IP-dip, which are optimized for 2PP. Alternatively, a custom route involves open formulations such as PEGDA plus a photoinitiator and crosslinker. Substrate selection depends on the structure's geometry. Use a 170 micrometer borosilicate glass cover slip for flat, high-resolution structures and fused silica for taller ones. Always use treated glass for fragile structures. The adhesion routine is a 4-step process: clean the cover slip, apply adhesion treatment, drop cast the resin, and mount for printing. This objective matrix shows configurations for different structure types. For high-resolution flat structures, use oil immersion and IPL resin. For high-resolution tall structures, use DIL and IP-dip. IPL is generally better for flatter, high-resolution structures, while IP-dip suits taller ones. Finding the optimal laser dose is critical. Too little dose leads to underpolymerization and broken walls. Too much dose causes swollen features and loss of resolution. Start with a small power speed matrix whenever you change the resin or objective, using literature values as a guide. The printing process uses voxel by voxel execution, where polymerization only occurs at the focal voxel when the 2-photon dose threshold is exceeded. The structure is written entirely voxel by voxel or block by block. Splitting large structures can reduce time, but may introduce stitching artifacts. To remove unpolymerized resin, commercial acrylates require development in PGMEA for 20 to 25 minutes, followed by an IPA rinse for 5 minutes. Custom PEGDA resins use 2-acetoxy-1-methoxypropane for 30 minutes, followed by a rinse in 2-propanol for 10 minutes. Capillary forces during drying pose a threat, capable of collapsing high aspect ratio features. Robust parts can use an IPA rinse and gentle gas drying. Slender or fragile structures require a lower surface tension exchange fluid, such as a Novex 7100 rinse after IPA to reduce collapse. Avoid aggressive air or nitrogen on delicate structures. Optional surface post-processing steps include oxygen plasma to activate the surface, UV post-cure to enhance structural integrity by raising cross-linking density, and various coatings like metallization for functional applications. Protocol A, using commercial acrylates, involves exporting CAD as STL, setting slice/hatch around 0.3/0.2 micrometers using a 170 micrometer borosilicate cover slip and IPL 780 resin. Start at 20,000 micrometers per second with moderate power, develop in PGMEA, rinse in IPA, and dry carefully. Protocol B, for custom PEGDA resin, requires preparing the specific resin mixture, drop casting on glass, and printing with an oil objective. Explore a power range of 10 to 50 milliwatts and a speed of 1 to 20 millimeters per second. Develop in 2-acetoxy-1-methoxypropane, rinse in 2-propanol. This protocol offers greater control over network chemistry. Troubleshooting common failures includes addressing poor adhesion with treated glass, reducing slice/hatch spacing for porous walls, and adjusting laser dose for swollen features or incomplete curing. Use low surface tension solvents for fragile parts to prevent capillary collapse, and optimize large solid parts with shell and scaffold approaches.